Okay, let's start our discussion of our next topic, which is stereochemistry. So to start out, let's quickly review what we know about isomers. So if two molecules or more than two molecules are related to each other as isomers, that means that they have the same molecular formula. So a pair or a set of isomers has the same molecular formula. We've already seen constitutional or structural isomers. So because they're isomers, they have the same molecular formula. Because they're constitutional isomers, they have a different connectivity, the order in which the atoms are bonded to one another. So different connectivity. And then what we saw in the last packet relating to stereoisomers. So we can define stereoisomers as having the same connectivity, but a different spatial arrangement of the atoms. Okay, so molecules can be related to one another as stereoisomers, but the particular type of stereoisomer could differ depending on the relationship. So two molecules might be enantiomers of one another. That's a relationship, a stereochemical relationship. Or they could be diastereomers of one another. So enantiomers and diastereomers, which we'll define later, are specific examples of stereoisomers. Now, before we get too far into this, let's think about why it's important. Why do we care about this at all? And one of the classic examples of this and of the importance of stereochemistry comes from this molecule, which is called thalidomide. Okay, so thalidomide was a drug that was prescribed in Europe in the late 50s and early 60s to pregnant women, and it was used as a sedative and as an antidote for morning sickness. So what happened was, as it turned out, in the structure of thalidomide, this carbon right here has a particular feature associated with it. So this is an sp3 carbon that has 4 different things attached to it. So that's what's known as an asymmetric carbon. So asymmetric carbon or chirality center. Okay, so an sp3 carbon that has 4 different groups attached to it, you can call either an asymmetric carbon or a chirality center, and those terms are completely interchangeable. So thalidomide has one of these. What that engenders is that there are 2, we can call them versions of thalidomide. Now, one of the versions of thalidomide was okay. It didn't cause any problems. The other version of thalidomide did. It ended up causing birth defects in the babies that these pregnant women eventually ended up delivering. And so the birth defects were things, you may have heard this in a biology class in the past or in some other context. The birth defects were pretty horrifying. There were things like missing limbs, deformed limbs, and other things. So as soon as they figured this out, this drug got pulled from the market. Now, the problem with it is that you can't just make one of the versions of thalidomide and administer that to a pregnant woman. Because of another feature of this compound, one version will change into the other version at physiological pH. So once it gets into your body, it's going to flip to the other version. That's not true for all such compounds, but it was true with thalidomide. And so what that means is that thalidomide cannot be safely administered to pregnant women. If you're not pregnant, it's safe. You can use it for other things, just not this. So the person who ended up blowing the whistle on this or pointing this out to people was this lady, Frances Oldham Kelsey. She was a reviewer for the FDA at the time, and she was the one that came out and said, hey, I don't think we should be marketing this. This is not a safe drug. And so it got pulled before we had a lot of the problems in the United States, the way that they did in places like Germany back in that at that time. So her actions and subsequent discoveries and subsequent investigation changed the way that the FDA reviews drugs. Okay, so they have to look specifically at how a particular stereoisomer of a drug is going to interact with your body before they can approve it for use as a pharmaceutical. So the stereochemistry of a compound dictates how it's going to interact or not interact with various receptors in your body. So for anyone interested in medicine or pharmacy, this is the main reason why we're interested in stereochemistry. So let's start by looking at a really important definition, and that is, what is a stereocenter? So a stereocenter is also known as a stereogenic atom. So you may see that term as you read or look at stuff online. So let's go ahead and define it, and then we'll look at some examples so that we can determine by looking at a structure if a particular atom is a stereocenter or not. A stereocenter is an atom at which the exchange of two ligands results in a different stereoisomer. So let's write all that down. Make sure we understand all the terms in the definition, and then we'll look at some examples and just apply the definition. So an atom at which the exchange of two ligands results in a different stereoisomer. Okay, so the term that might be unfamiliar to you, you may or may not have heard this in Gen Chem, is the term ligand. Ligand is a chemistry word that just means a group of atoms or an atom that's attached to some central point of interest, some central atom. Okay, so let's take this definition for a test drive and see what we can make of it. Let's look at this compound. It's going to be an alkene. And we're going to look at this carbon atom and ask the question, is this a stereocenter? So is this carbon a stereocenter? Okay, so according to the definition, what we would need to do is mentally switch the positions of two of the groups that are attached to that carbon. So we're going to mentally swap the places of two of the groups. Now the two groups, in this case, would be the methyl group and the hydrogen. So I'm going to put the methyl group where the hydrogen was and put the hydrogen where the methyl group was. Everything else in the structure, I'm leaving the same. Okay, so the carbon that I highlighted in the original structure is a stereocenter as long as the new structure that we just drew is a different stereoisomer than what we started with. So let's look at that. So remember, in an alkene, so I'm drawing a dashed line across the double bond in each case. You can't rotate around a double bond. Remember that the p orbitals that are overlapping, one on each of the carbons in the double bond, if we tried to rotate around that double bond, the bond would break. And so there's no rotation around a double bond, which means that the positions of the groups, the spatial arrangements of the groups, are fixed in position. So in our original structure, we can't rotate around the bond, so that means that those methyl groups are never going to be on the same side of the double bond or the same side of that orange dashed line that I've drawn. Because they're on opposite sides, we would call that a transalkene. So this is a transalkene. Once we switched the two groups, though, they ended up on the same side of the double bond. And so now we're looking at a cisalkene. Trans and cis reflect different spatial arrangements, but the connectivity is still the same. groups are attached in the same places that they were before we made the switch. And so yes, the carbon atom that I highlighted is a stereocenter. And we could be a little more specific and say it's an sp2 stereocenter because of the hybridization of that carbon. Okay, let's try another one. Okay, so this will be one involving a cyclohexane ring. So it's going to kind of go back or refer back to what we did in packet 4 at the end. So here's a 1,4-dimethyl cyclohexane. And so what we're going to do is examine the carbon atom that I've highlighted to try to figure out if it's a stereocenter. Now that is an sp3 carbon. So remember that for an sp3 carbon, to show the tetrahedral geometry, we're going to have 2 bonds in the plane, 1 forward and 1 back. In this structure, at that carbon, the 2 bonds that are in plane are shown already. The one coming forward is to the methyl group, that's shown. The one going back is not shown, and so that must be to a hydrogen. So we'll do the same thing we did up above, which is to mentally exchange 2 of the groups. So we'll switch the position of the methyl group and the hydrogen. So now the methyl group will go back and the hydrogen will come forward. Okay, so have we generated a new or a different stereoisomer? Well, if we look at the starting structure, the first structure, the methyl groups are on the same side of the ring. That is cis. In the second structure, one of the methyl groups is up, the other one is down, so they're on opposite sides of the ring. So that's trans, which means yes, by switching the positions of 2 groups, we've generated a new stereoisomer. So we could say here, yes, this is an sp3 stereocenter, which we can also call a tetrahedral stereocenter. Okay, let's do a little summary over here. The broad category, stereocenters, which we defined up above. And we saw 2 versions. We saw sp2 stereocenters, which we're probably not going to deal with a lot. And we saw an sp3 stereocenter, or a tetrahedral stereocenter. But we're also aware from the previous page of something that's called an asymmetric carbon, or a chirality center. Again, those terms are totally interchangeable. So a chirality center is a specific example of an sp3 stereocenter. So not all sp3 stereocenters are chirality centers, but some of them are. And those are the ones we're going to be focusing on. So let's take a look at some examples of compounds that have asymmetric carbons in them. Okay, so let's take a look at this carbon here. It's an sp3 carbon, so to draw it with some stereochemical perspective, 2 bonds in the plane, 1 forward, 1 back. Okay, so if we look at that carbon, we see that it's attached to an OH group, a bromine, a hydrogen, and a methyl group. So those are 4 different groups, and so this is an asymmetric carbon. Let's try another one. Let's take a look at this alcohol. So I'm going to number the carbons from left to right. So at carbon 1, if we inspect all of these carbons, at carbon 1, we know that there are 3 hydrogens. Okay, so you don't have 4 different groups. So carbon 1 is not an asymmetric carbon. At carbon 2, remember that we have 2 bonds in the plane. Those are shown. A bond coming forward, and then there's a bond coming back, or going back. Because it's not shown, it must be to a hydrogen. Carbon 2 has the OH group. It has the hydrogen. It's attached to carbon 1, which is a methyl group, and it's attached to carbon 3, which is a part of a propyl group. So carbon 2 does have 4 different groups attached to it, which makes it an asymmetric carbon. Carbon 3 has 2 hydrogens, so it doesn't have 4 different groups, not an asymmetric carbon. Carbon 4, same thing, not asymmetric. And carbon 5 is in the same boat as carbon 1. It has 3 hydrogens, therefore it's not an asymmetric carbon. Okay, let's try an example that's a ring. Okay, so the carbon we suspect of being an asymmetric carbon is the one that I've highlighted. So remember, you want to include, if there are hydrogens not drawn in these early stages before you get used to this, you're going to want to draw in all the bonds that are not explicitly shown. So what we would do to compare the groups is to move directly away from that asymmetric carbon. So we have the hydrogen, we have this carbon that's involved in a double bond, and then we have these 2 carbons, which are part of the ring. Clearly, the hydrogen and the carbon involved in the double bond are different from one another, and both of those things are different from the carbons in the ring. Both of those ring carbons are CH2s. So they're the same, but we're not done. We need to move out another bond. So we continue away from the asymmetric carbon, we continue moving away from the asymmetric carbon around the ring in both directions. And what we get, or what we get to, I should say, is this carbon over here, which is connected to an oxygen, and this carbon here, which is not. So right away, that breaks the tie. This means that the carbon that I originally highlighted, this guy down here, is an asymmetric carbon. So what you want to do is keep moving away from the carbon you think is asymmetric. Okay, whether that's around a ring like we did here, or down chains, so you might have a carbon that has some long chains attached to it, and you want to figure out if they're the same or different. You would move down the chain, both of those chains, until you find a difference. So keep moving away from the carbon you think is asymmetric, either around a ring or along chains, until you find a difference. Or see that there is no difference. If there is no difference, that means you have 2 of the same group attached to that carbon, so it's not an asymmetric carbon. Let's go back to an example we did up above. So let's look at our original 1,4-dimethylcyclohexane. This was a cis version. And remember what we did with that structure is we looked at this carbon down at the bottom here to determine if it was a stereocenter. Okay, we found that it was a stereocenter. But now let's see if it's an asymmetric carbon. So it is a tetrahedral stereocenter, but is it an asymmetric carbon? So again, let's include the hydrogen that's not shown. And then starting at the asymmetric carbon, attached to it, we have hydrogen and methyl. Those are different. And then these two ring carbons. The two ring carbons are the same. So we need to continue moving away from the asymmetric carbon around the ring. So we go one bond further in each case. And again, we end up with a tie. These are both CH2 groups. So we continue moving out, and we get to the same place. In other words, we can't break the tie. So what we can conclude here is that although the highlighted carbon, the yellow highlighted carbon rather, is a tetrahedral stereocenter, it is not an asymmetric carbon. Because it doesn't have 4 different groups attached to it. The good news is that 99% of the time you're looking for asymmetric carbons. And so if you can learn to recognize those, that's going to be a lot of it right there.